This is my second attempt at standard 1.3. For the second time I decided to do problem 1.16, which said that we are given spin components of a beam of atoms are prepared in the state phi n and are measured, and the following experimental probabilities are obtained, which are these ones right here. Let's see if I can zoom in a little bit for you. Too much. There we go, that's better. Alright, so we see these are the probabilities that are obtained, and we're asked to determine this input state up here. So the probability of obtaining the eigenvalue an and a measurement of the observable a in the system in the state phi is found by this formula right here, where the value, where the vector an is the normalized eigenvector of a with regard to the eigenvalue an. So we can start off by letting the input state just be an arbitrary state with coefficient a and b, where a and b are both constants. We can use our experimental values and the definition of the probability to solve for the constants. So starting with the probabilities on the z-axis, which is just the plus and minus, we can solve for a and b. When we solve for this, we get a equals 1 over square root of 2, and b equals 1 over square root of 2 times e to the I theta. The reason we can do this is because we can set, there should be e to the I theta in front of a, or in the a value, but we can set that to 0, and then let the theta and b just be an angle with respect to a. So then moving on, we try to solve for theta using the other probabilities and the same method that we did to solve for a and b, but now I want to solve for theta, this theta right here. So start with the positive x value. We have 3/4. Just working through the math, pretty simple. We get down to theta equal to pi over 3. So that is what we get for p in the probability in the positive x-axis. Then we do, then we can do the positive y-axis right here. We plug in our probability that we're given for 0.067. Again, we just work through the same steps as before, and what we get down to is theta equals negative pi over 3. Then we do the same thing for the negative x-axis, same problem, work through, and we get theta equals pi over 3. And then we do it one last time for the negative y direction, and we get negative pi over 3. Important thing to notice, for the x values, we notice that we always get cosine of theta when we're solving for the for the theta angle. And if we notice for the y values, we get the sine inverse. So because cosine is an even function, cosine of pi over 3 is equal to cosine of negative pi over 3. And since we got negative pi over 3 for the y values, which are dependent on sine, which is not even, we can just set theta equal to negative pi over 3, and it will work for all 4 situations. Thus our input state is this right here, with theta equaling negative pi over 3. And that is how we solve problem 1.16.